Imagine this, Tonite. You look up at the sky. You see stars. Thousands of them. But what if I told you every single star you see is already in the past? You are not looking at space. You are looking at history. And the moment you try to cross that history, to travel to another star, the universe slams a door in your face. Not gently, violently. Today's question, why is interstellar travel impossible? And what would Richard Feynman say that completely shatters your sci-fi dreams? Let's begin. The dream that refuses to die, humans have always wanted to go further. From crossing oceans, to landing on the moon, to sending probes beyond Pluto, we believe, if we can imagine it, we can build it. Science fiction tells us. Warp drives, wormholes, hyperspace jumps faster than light engines, but physics doesn't care about dreams. Physics cares about rules. And one man changed everything. The speed limit that breaks all hope in 1905. A quiet patent clerk named Albert Einstein published a paper that quietly destroyed interstellar travel forever. Special relativity. The most brutal sentence in physics. Nothing with mass can reach the speed of light. Not very hard. Not needs better technology. Not maybe in the future. Impossible. Why? Because the universe has a built-in speed limit. 2,997,92458 meters per second. The speed of light, and it's not just about light, it's about causality, it's about reality itself. Why can't we just go faster? Let's say you build a spaceship, you keep adding fuel, you keep accelerating. Newton would say more force, sight you more speed. But Einstein says the faster you go, the heavier you become. Not emotionally, your mass increases relative to an outside observer. As you approach light speed, your mass increases toward infinity time, slows down length, swinged, contracts to reach light speed. Your mass would need to become infinite, and infinite mass requires infinite energy, and infinite energy doesn't exist. Feynman's brutal simplicity now enter Richard Feynman. Feynman had a gift. He could explain terrifying physics in childlike clarity. He once said, "It does no harm to the mystery to know a little about it, but sometimes knowing more makes things worse." Feynman emphasized something devastating. The laws of physics are not suggestions. They are not negotiable. They are not impressed by ambition. They are mathematical. And mathematics doesn't care about hope. The scale problem when it talks about. Let's look at reality. The nearest star system, Alpha Centauri, distance 4.37 light years, meaning even if you could travel at the speed of light, which you can't, it would take 4.37 years. But realistic speeds, our fastest spacecraft ever built. Voyager 1 speed, about 17 kilometers per s. At that speed, reaching Alpha Centauri would take over 70,000 years. That's longer than recorded human civilization. That's just the nearest star. Milky Way, 100,000 light years. Interstellar travel isn't hard. It's absurd. Energy, the ultimate law. Let's talk numbers. To accelerate a modest 1,000-ton spaceship to near light speed, you would need energy comparable to the total energy output of humanity for centuries. And that's just to accelerate. You also have to slow down, protect against radiation, avoid microscopic dust grains that hit like nuclear bombs at relativistic speeds at 99% light speed. A grain of sand equals catastrophic explosion. Space is not empty, it's lethal. 4. The illusion of just better technology, many people say. We'll invent something better, but Feynman warned about this kind of thinking. Technology improves within the laws of physics. It does not rewrite them. You can invent better engines, better materials, better reactors, but you cannot invent a universe where 2 plus 2 equals 5. And you cannot invent a universe where mass can outrun light, unless the laws themselves are wrong. But every experiment for 100 plus years confirms they're not. What about wormholes? Yes, wormholes are mathematically allowed in Einstein's equations. But here's the catch. To keep a wormhole open, you need exotic matter, matter with negative energy density. We have never observed it in usable quantities. Even quantum effects that produce tiny negative energies, like the Casimir effect, are microscopic. You would need astronomical amounts. It's like saying, yes, teleportation is possible if you have a dragon's heart and a black hole in your pocket. Mathematically possible, twain physically practical. Time dilation for the psychological trap here, where things get weird. If you travel at 99.9% light speed, from your perspective, time slows down. You might experience 5 years, Earth might experience 100 years. So in theory, you could reach distant stars within your lifetime. But here's the cost. Everyone you love would be dead when you arrive back. Interstellar travel becomes one-way exile, not exploration. Exile free. The deeper reality Feynman knew something profound. Physics is not about what we want, it's about what is. And what is terrifyingly constrained. The universe is not built for travel between stars. It is built for stability, structure formation, causality, the speed of light. Isn't just a number, it's a structural feature of spacetime. Break it, and you break cause and effect. If faster than light travel were possible, you could travel into the past. You could create paradoxes. You could destroy logical consistency. The universe prevents that, not with force, with mathematics. The harsh truth interstellar travel faces 4 unbreakable walls. The speed of light, limit, infinite energy requirement, relativistic hazards, causality, paradoxes. This isn't pessimism, it's physics. And Feynman would smile and say, the universe is under no obligation to make sense to you. But it does make sense. In that sense, says the stars are not meant to be reached. The speed of light, energy limits, relativistic destruction. But what if that's only the surface? What if the real reason interstellar travel is impossible is not speed? What if it's information? To understand this, we need to go deeper than rockets. We need to go into the fabric of reality itself. And once again, we follow the thinking style of Richard Feynman because Feynman didn't just study particles. He studied how nature computes. The universe is not made of things. Here's the first illusion that must die. The universe is not made of solid objects, it's made of fields. In quantum field theory, electrons are excitations of an electron field. Photons are vibrations in the electromagnetic field. Even empty space is not empty, it's boiling. Virtual particles pop in and out of existence constantly. What we call matter is a stable pattern in a restless ocean of probability. So when you say, I will travel to another star, what you're really saying is, I will move an organized pattern of quantum information across cosmic space-time. And that is astronomically harder than moving a rock go. The Heisenberg problem, enter Werner Heisenberg. The uncertainty principle. You cannot simultaneously know exact position, exact momentum. The more precisely you define one, the less precise the other becomes. Now imagine accelerating a spacecraft to near light speed. To control it precisely, you must know its position exactly, know its velocity exactly. Quantum mechanics says, number, there is always fuzziness. At small scales, precision collapses. At relativistic scales, energy amplifies quantum fluctuations. So the faster you go, the more quantum instability you amplify. The universe becomes noisier, not smoother. When the vacuum isn't empty when traveling near light speed, something terrifying happens. From your frame of reference, the vacuum ahead of you becomes compressed. Quantum fluctuations increase in energy. Space itself becomes more violent. The cosmic microwave background radiation, harmless at rest, becomes high energy radiation in your frame. At 99.999% light speed, background photons turn into lethal gamma rays. Space becomes a radiation furnace. The universe was not designed for relativistic cruising. It actively resists it. Feynman's path integral 40. The nightmare version Feynman developed something revolutionary. The path integral formulation of quantum mechanics. Instead of particles taking one path, they take every possible path, all of them simultaneously. And reality is the sum of those probabilities. Now think about a spaceship. To go from Earth to Alpha Centauri, it must follow a classical trajectory. But quantum mechanics says there is no single trajectory. There are infinite possible histories. At macroscopic scale, probabilities align to produce stable paths. But at extreme energies, quantum probabilities become less predictable. The more energy you pump into a system, the more violently quantum fluctuations respond. Interstellar speeds require extreme energy. Extreme energy amplifies quantum chaos. The universe becomes statistically unstable. Space-time is not a highway. Here's another illusion. We imagine space like an empty road. You just drive farther. But according to general relativity, space-time is dynamic. It bends, it curves, it responds to energy. Add enough energy to accelerate a massive ship, and you curve space-time around it. Add too much. You risk gravitational collapse. If energy density becomes too high, you don't get a faster ship. You get a black hole. The energy required for near light travel begins approaching levels where gravity fights back. The universe says, you want more energy, fine. I'll give you curvature. The information density limit, now we reach something deeper. There is a maximum amount of information that can exist inside a given region of space. This is hinted at by black hole thermodynamics and entropy limits. If you compress too much energy or information into space, it forms an event horizon, meaning there is a limit to how densely reality can be written. Interstellar travel requires massive energy concentration, massive information, stability, massive shielding. You're pushing against the maximum storage capacity of spacetime itself. It's like trying to overclock the universe. Eventually, it overheats. The cosmic speed limit is an information limit. Here's the twist. The speed of light is not just about motion. It's about information transfer. Nothing can transmit information faster than light. Why? Because causality must remain intact. If information travels faster than light, effect could precede cause. You could send a message to your past self. Reality would fracture into paradox. The speed limit is not about photons. It's about logical consistency. The universe enforces consistency at all costs, even if that means locking you inside your solar system. Energy vs. control. Let's assume impossible technology, infinite fuel, perfect materials. Even then, to travel safely between stars, you must maintain control over position, shielding, navigation, structural integrity, quantum coherence of matter. As speed increases, tiny uncertainties become catastrophic. A microscopic navigation error over light years. You miss the star by billions of kilometers, a tiny shielding flaw. Radiation sterilizes the ship. At relativistic speeds, there is no room for error, and quantum mechanics guarantees error, not engineering error. Fundamental error. Fundamental error, fragility. Now consider something uncomfortable. Humans are warm, wet, quantum-sensitive systems. Our brains function via delicate electrochemical processes. High energy radiation breaks DNA, destroys neurons, induces mutation. Even minor cosmic radiation is dangerous on long missions. At relativistic speeds, it's apocalyptic. You would need shielding so massive it defeats acceleration feasibility. Again, energy versus mass versus speed versus radiation. It's a closed trap, the psychological illusion of scale our brains evolved for. Walking distances, tribal territories, planetary surfaces, not light years. A light year is 9.46 trillion kilometers. The nearest galaxy, Andromeda, 2.5 million light years. Even if you traveled at light speed, you would arrive long after human civilization has changed beyond recognition. Interstellar travel is not exploration, it's time abandonment. The universe may be discrete. Some physicists suspect space-time itself may be quantized at Planck scales, meaning there's a smallest unit of length, a smallest unit of time. If that's true, then smooth motion at extreme scales breaks down. At ultra, high energy densities required for near light speeds. You may begin interacting with the granular structure of space-time, like hitting pixels on a screen. And we don't know what happens there, but we know this: Planck scale. Physics is not friendly to macroscopic stability. The deeper Feynman lesson. Feynman once said, "Nature uses only the longest threads to weave her patterns." The threads of nature are quantum mechanics, relativity, information theory, thermodynamics. Interstellar travel tries to stretch all of them simultaneously. And each one pushes back. It's not one wall, it's a cage. A perfectly consistent, mathematically elegant cage. Now we face the final uncomfortable truth. What if interstellar travel isn't impossible because we lack technology, but because the universe was never designed to allow it? Not by conspiracy, not by intention, but by structure. And if there's one physicist who would force us to face that structure without fantasy, it's Richard Feynman. Because Feynman believed in something ruthless. The test of all knowledge is experiment. And every experiment says the same thing. The universe allows observation. It does not easily allow crossing. The expanding trap. Let's confront something most people don't realize. The universe is expanding, not slowly accelerated. This discovery, confirmed through supernova observations in the late 1990s, tells us something terrifying. Distant galaxies are moving away from us faster and faster. Some are already receding faster than the speed of light due to cosmic expansion. Not because they're breaking relativity, but because space itself is stretching. This means there are regions of the universe we will never reach. Not even in principle. Not even if we could travel at light speed. They are beyond the cosmic event horizon. Forever, the observable bubble, we live inside a bubble of visibility. Light from distant galaxies takes billions of years to reach us, but beyond a certain distance, light emitted today will never reach Earth. The universe is not just big, it is causally fragmented. There are galaxies that exist that we will never see, never reach, never interact with. Reality has built in separation. Even light is trapped. Think about that. Light is the fastest thing possible, and even light cannot conquer expansion, if even photons cannot guarantee contact across cosmic distances. What chance does a spacecraft have? Interstellar travel assumes a static arena, but space-time is dynamic. It stretches, it isolates, it pulls everything apart. Feynman's brutal honesty. Feynman despised comforting illusions. He would likely say, "You must not fool yourself, and you are the easiest person to fool." Science fiction fools us beautifully. It makes the galaxy feel accessible. But physics says the galaxy is barely accessible, the universe beyond it, functionally unreachable. The time wall lets assume something radical. You solve propulsion. You solve radiation. You solve energy. You reach another star in 20 years. Now what? Civilizations evolve, languages change, cultures transform. Even if physical travel were possible, meaningful connection collapses under time. Communication across light years has built-in delay. A message to a planet 100 light years away takes 100 years to arrive. A reply takes another 100. Conversation becomes archaeology. You are not exploring the present. You are interacting with the past. The biological clock problem, humans evolved for planetary timescales. Even with life extension, multi-generational shifts create sociological instability. Isolation produces psychological breakdown. Closed ecosystems drift biologically. Interstellar travel becomes not a journey, but an evolutionary experiment. And experiments fail. Nature is not optimized for species migration across light. Years it is optimized for local adaptation. Why is the universe so big then? This is the haunting question. If we cannot cross it, why is it there? Why billions of galaxies? Why trillions of stars? Why such obscene scale? One possibility: the universe is not scaled for travel. It is scaled for structure formation. Gravity requires vast distances in time to create. Galaxies, heavy elements, stable stars, planets, chemistry. Life, the vastness, isn't an invitation. It's a requirement for complexity. The anthropic angle. There's an uncomfortable idea in cosmology. The universe must be large for observers to exist. Heavy elements form in stars. Stars require cosmic time. Galaxies require gravitational collapse across immense scales. The universe isn't big for tourism. It's big so you can exist. The scale that blocks travel is the same scale that made you possible. Winnie, the simulation, thought, careful, some speculate. What if the universe is informational at its core, a computational structure? If so, constraints like speed of light information, density causality limits could be processing constraints, not barriers of metal and fuel, but limits of the underlying system. Even if this is speculation, the pattern remains. Reality enforces boundaries, hard ones. The prison or the sanctuary. Here's the psychological shift. We interpret limits as prisons. But what if they're stabilizers? If faster-than-light travel were easy, causality collapses. Paradoxes emerge, energy scales destabilize space-time. The same laws that trap us also protect consistency. The universe is stable because it is constrained. Interstellar isolation may be the price of coherence. The great silence, this connects to a haunting mystery. Where is everyone? If interstellar travel were easy, the galaxy should be teeming with visible civilizations. Yet we observe silence, perhaps not because life is rare, but because travel is impossible at meaningful scale. Civilizations remain isolated islands, born, evolving, extinct, without ever touching. The cosmos may not be empty, it may be disconnected. Feynman's final lesson. Feynman loved reality more than fantasy. He once said, "I'd rather have questions that can't be answered than answers that can't be questioned." Interstellar travel might be one of those questions, not how do we build it, but was it ever physically allowed? And the deeper physics suggests the universe is structured for locality, not traversal, for observation, not domination, for existence, not expansion. The ultimate perspective shift, maybe the dream of crossing the stars, is a projection of tribal migration instinct onto cosmic scale. We evolved to move, to explore territory, to expand. But the universe operates on principles far colder and more precise. It permits light, gravity, chemistry, consciousness. It does not easily permit relativistic mass migration. We are planetary beings in a relativistic universe, and that mismatch may be permanent. The final reality shatter interstellar travel is not blocked by weak engines, lack of funding, primitive material. It is blocked by space-time geometry, quantum uncertainty, energy conservation, information limits, cosmic expansion. 5 independent pillars, all aligned against the dream. When multiple fundamental theories agree on a limit, that limit is probably real.